So hello everyone. So in this video I am discussing the AC parameters of common drain MOSFET amplifier. So the drain terminal is connected to ground here. This is the DC supply VG in the AC unless it will connect to ground, right? The input is connected to the gate terminal and the output is taken from the source terminal. This is the common drain MOSFET amplifier. So first, if we discuss about the current gain, that is I naught upon IN. So because the input is applied at the gate terminal, so input current is the gate current, which is 0. So that's why here also the current gain is infinite, just like the common source MOSFET amplifier. And the input resistance is also infinite because input current is 0, right? So here also we have to discuss only these two parameters, that is the small signal voltage gain and the internal output resistance. So let's start with the small signal AC model drain amplifier. So the input is connected between the gate and the ground terminal, and this is the VGS, and here this is GM VGS and the source. Here now, when the capacitor will be short circuited, both these resistors will be in parallel. So the equivalent load resistance will be the parallel combination of RL and the source resistance, right? And the voltage is taken across it. This is the source terminal. This green terminal is grounded, and here also the drain current is flowing. Now the small signal voltage gain, so we will apply simply a KCL at the source terminal, right? V naught upon RL dash, then this current is incoming, so minus GM VGS and plus V naught upon L naught. So we have to replace this VGS, right? So VGS in terms of VIN and this V naught, will apply a KVL here, right? In this path. So from this KVL we can see that this input is equals to VGS plus V naught. So VGS is equals to VIN minus of V naught, right? So this is the relation. Now KVL, so KCL at the source terminal, so it will be V naught upon RL dash plus V naught upon R naught and minus VGS is equals to 0. So यहाँ पर this is the V naught 1 upon RL dash plus 1 upon R naught, then minus GM and VGS is VIN minus of V naught. So now this is again the parallel combination form, so we can write the equivalent resistance of these two parallel resistors, that is the RL double dash, and यहाँ पर this is the plus GM V naught and equals to GM VI, right? So V naught, and this will be 1 upon RL dash plus GM, so 1 plus GM RL double dash upon यहाँ पर GM VI. So V naught upon VI, it is the small signal voltage gain, is GM RL double dash upon 1 plus GM RL double dash. So this is the small signal voltage gain of one drain amplifier, and this RL double dash is the parallel combination of RL dash and R naught, and RL dash is RL parallel RS parallel with R naught, right? Now this voltage gain is GM RL double dash upon 1 plus GM RL double dash. So if this RL and this R naught, if this RL is infinite and this R naught is infinite, which means the lambda is equal to 0, right? So if this is the case, so the RL double dash will be simply equals to RS, right? In that case, the AV is simply GMRS upon 1 plus GMRS, right? And if this GMRS is very greater than 1, which is in most of the cases, so the small signal voltage gain will be simply equivalent to 1, right? So that's why the common drain MOSFET amplifier is the voltage buffer circuit, or the voltage follower circuit we can say, And this means that there's the V naught upon Vi is almost equals to 1, right? So means the V naught is almost equals to Vi, and because the output we have taken from the source terminal, so this we can write like this: Vs is almost equals to Vi, and that's why the common drain MOSFET amplifier is known as the source follower circuit, because the source voltage follows the input voltage, right? It is the source follower circuit. Source follower circuit, and because the output is taken from the source terminal, so source voltage is following the input voltage. That's why the source follower circuit, right? So this is the small signal voltage gain and the approximation, right? Now for the internal output resistance. So internal output resistance, we have to again draw the small signal model by removing the input supply VDC upon IDC when the input is 0. So input is 0, so simply dot submitting input. So this is the VGS, and now here we will connect the VDC, the current flowing. This is IDC. So this is the ID current, and this current is flowing in this direction ID, right? And this ID is equals to minus of IDC, and this VGS, we can see that यहाँ पर this VGS is equals to minus VDC, right? So VGS is equals to minus of VDC. Now again we apply a KCL at the source terminal. So KCL at the source terminal, it will be VDC upon this R0, VDC upon R0, then minus GM VGS, right? And VGS is minus VDC, so it will be plus GM VDC, and then this current is incoming, so minus IDC is equals to 0, right? So VDC and half of this is the 1 upon R0 and plus GM is equals to IDC. Now this GM we can write like this: 1 upon R0 plus 1 upon GM, as I have performed in the diode connected transistor. So same format. So now this will be the parallel combination R0 parallel with 1 upon GM, right? So VDC upon IDC, which is the R0, is simply R0 parallel with 1 upon GM. So this is the internal output resistance R0 parallel with 1 upon GM. So R0 is equals to R0 parallel with 1 upon GM. Now this R0, that is 1 upon lambda ID, it is having a value, right? In GM, let's take the value just like 50 milliampere per volt. So 1 upon GM will be 1 upon 50, and this will be, right, so 20 ohm, right? So it is always higher than this 20 ohm. Obviously this R0 is having a high value comparative to this 1 upon GM. So the parallel combination of this R0 parallel with 1 upon GM will be approximated to 1 upon GM, right? So this is the approximation. So this is how we can analyze the IC parameters of common drain MOSFET amplifier, the voltage gain and the internal output resistance. Okay, thank you.